again is where, kind of right in the middle here. This is typical. Now we're in our climate zone here. I have a trusty ice cookie. I'm really glad there's a little mini market across the street. I don't know where I would get ice otherwise. Now, of course,
you lost a piece of ice.
What we're doing here is, of course, we're creating the polar ice cap. So even though this is not actually the North Pole, we're creating the same idea. We're putting some cold up here.
Lost an ice cube. In the tank.
Oh, in the tank.
Not two.
That's big. Water in there. Okay, now under this regime, get used to this rotating frame of reference. Okay, now under this regime, the driving force is the same, so it's still, in principle, just this going on now. But we expect, we talked about in class, you guys have the advantage in this section of having gone through the full lecture, which is, by the way, it's going to make this lab go faster, which we should be done here pretty soon. That we're going to see the same general pattern, which is the water's starting to drop, it's heading off to the right, rising, coming back in the. But now, as that current heads over there, I said it's unstable. It's baroclinically unstable. And it's going to go into oscillations. And in fact, what I say, when it gets very unstable, it can pinch off gyres, right, and vortices. So that's our hypothesis is that from our class discussion, we said that at higher latitudes, higher rotational rates, the system becomes inherently unstable. We should see oscillations rather than just smooth tones. So we're going to expect to see some kind of oscillating pattern in here. And it's oscillating such that after a while, it's actually going to start to form little rings. And if we wait long enough, we should see actually fairly stable rings that are not going anywhere. They're traveling. The ring is part of the solid body, as it were. But within that, there's a second rotation. So we end up with two rotational scales. The large-scale rotation and then a slower rotation within the rings, which is the same thing as we were talking about in class. We said, like a hurricane. A hurricane rotates on its own axis and a different speed than what the Earth is rotating, so you get two different rotations. So that's what we're going to do here. We're going to create some little cyclones, if you will, and little anticyclones, some little mini hurricanes. Okay, really more like not hurricanes, but mid-latitude cyclones. Okay, an anticyclone. Okay, so let's see how we're doing. We're going to visualize it the same way. We just expect to see different visuals. Again, first of all, you're going to see different behavior right off the bat. It's a lot more stuff going on. But ignore the initial little tendrils, because to some extent they're just an artifact of the dropping particles. Give it a minute to develop. Oh, actually, we're getting some useful action here. What's forming?
Ring, yeah.
Spiral. Whoa, this is totally different. In fact, it's not even all that obvious that the stuff is. I mean, over long term, we're going to see the dye curving off to the right, but it doesn't even look like it's curving off to the right. It's getting entrained into. Now, these things here, this is where you definitely want to get close, right? Especially right in the next couple minutes while these are very clear. You're getting a lot of structure there. It's almost like a column, right? And if you look at that spiral, it's like a vertical column of dye with amazing amount of pretty organized structure. There's about three of them forming right now. Those are called Taylor columns. Another thing you can throw into your write-up. Taylor. They're named after a famous fluid mechanics guy named G.I. Taylor. I don't know what G.I. stands for. He's always named in the books as G.I. You can look him up on Wikipedia. Anyway, Taylor was this British dude who explained the fact that these spirals form in tight columns, nice, almost perfect coffee can kind of columns, and they're named in his honor. They're called Taylor columns.
There's probably some peer-reviewed journal articles.
Oh yeah, that's good. Yeah. Example, yeah, you could look up Taylor columns. You'll find. Try to find one you can understand. Okay. But there are bound to be some elementary explanations for Taylor columns. Yeah, and look for like peer-reviewed type thing, or the introduction, or like, well, as everyone knows who's going to read this article, this is what a Taylor column is. Okay. Anyway, so yeah, we're seeing, and this is where the rotating frame of reference, the camera, really is particularly helpful because it really enables you. Otherwise, it's very hard to see the secondary motions in the vortices because you're too busy looking at them going around. But when you freeze, notice that the vortexes are not moving as fast as, the vortexes have their own rotational rate within the greater rotation. Okay. And now what is the relevant, velocity now? It's not the same as it was earlier. In fact, it's probably slower. If you look because inside those vortexes, the water is actually probably going slower than it was when it was in the simple Hadley cell. So let's see what the top is doing, if that's doing anything. Before, when we did this, we saw the top moving in a pretty obvious, organized way around. Is that what's happening now? The dots moving in an obvious, coordinated fashion. Remember last time they were going, which way it was? The bottom was going clockwise, and they were going counterclockwise. Now notice that, so that obvious vertical, and what it amounts to is, since most of this motion is going into these Taylor columns and vortices, all the dots are doing, if you watch them really carefully, you'll see that they're very slowly rotating around in the vortex, but the motion is so slow. If you watch these for a minute, see how they're just tracking that vortex that's below them, that Taylor column that's underneath them. So they're not going around anymore. So we don't have a nice organized flow here. What we have is a very, very sort of chaotic at one level, but then organized in a different way. I mean, this looks utterly different than what we saw a few minutes ago. Right? And so everybody get a look at it here.
They're kind of tending to move outward, though, aren't they? That does not sound like it.
Yeah, there's still a driving force outward. Obviously, the die has been carried. Oh, yeah, this is a good one here. Yeah, here's a nice jet stream oscillation there. Notice how it's basically going out and gone out towards, and then now see how it's swinging back towards the eyes. But now it's going away from the eyes. There's your oscillating jet stream. So what it's doing is it's heading towards 30 degrees latitude, then it heads north towards 60, but now it's curving back. So this is, you can't really predict what it's going to do next very well, and that's why the weather is so much more unpredictable in the temperate zone. In the tropics, you pretty much know what's going to happen. There's a dry season and a wet season, and that's about it. We have bright sunny day today, rainy day tomorrow.
So you said that would be like kind of where it pinched off because it oscillated and then.
Mm-hmm. Yeah, and in fact, you can see it in that one. Notice how it oscillated, and now it's looks like it's what they call shedding. This is a good one. Eddy shedding is what that's called. When you get a jet motion that sheds an eddy. Say that 5 times fast. Eddy shedding, eddy shedding, eddy shedding. Okay, so we're shedding eddy. But yeah, you can see now that's the classic oscillating jet stream sort of pattern there. And as always, we can make so the dots aren't too interesting actually in this case, but the green dye. Well, what do we expect to see when we look at the vertical structure now? We expect to see, before we saw a great big giant spiral all the way to the bottom. What do you expect to see now? Do you expect to see one big spiral to the bottom? Well, we see what's going on at the bottom is these whirls and things.
Fine.
Oh, there it is. That would take a while. This came close. I'm glad this isn't acid. Okay. I'm going to do it in a couple different locations. But this part of the experiment, it turns out it's tempting to put a lot of dye in, but that's exactly the opposite of what you want to do. It gets messy up there.
Wow.
So actually, you give it a second to develop, and then this is a good one to come over and stick your head over it as they start to form. Oh, now it's starting to do something. What we expect to see is basically, again, the dye get caught up in eddies and swirl around itself and follow. Oh yeah, look at a nice trail across there. Basically big oscillating patterns that then get swept into circular eddies. This is pretty cool. You definitely take a look at this. This is trippy. This one here in particular. Yeah, and the camera. Oh yeah, the camera is really helpful. That one I got. You know, like I say, it's just kind of luck whether you get the dye in the right spots. But that one right under Tim's arm. Pretty good. So interestingly, I would think that if you look at the speed at which these vortices are moving, it's definitely less than a centimeter per second now. You can either actually maybe the camera's easier. They're moving really pretty darn slow. So the currents that are induced in the system, you might say, well, why should there be a difference? What it amounts to is it's the same amount of energy. This is the same thermal gradient. It's just now all that energy is being turned into a bunch of vortices. So since energy is conserved, I guess one way of thinking about it is if you have a bunch of vortices, they're all going to turn slower than if you have one big vortex. So when we had one big vortex like the Hadley cell, it moved along at a pretty good clip, about a centimeter per second. When you divide it up into a bunch of vortices, each of them only has the same amount of energy divided up, so each of them moves slower. Okay. So it's kind of counterintuitive because you think, oh, everything ought to be going faster here, and it's like, no, it's just more chaotic, it's more randomized. Okay. Although in the end, there is a lot of structure in the sense that these eddies have a lot of structure to them. And again, now our Taylor columns are a combination of pink and blue. But also, notice how much more the dye has distributed itself over the whole tank in the same amount of time. Last time, remember, the dye was all still kind of stuck on the bottom. Now, this whole tank is getting pretty purpley everywhere. And that's because we are getting better. This chaotic motion is also mixing the air a lot better than that very simple, smooth flow we had in the Hadley cell. So you expect to see, and from the Earth's perspective, what does that mean? That means cold air and warm air is mixing more efficiently. Well, that's good for us who live up here at 45 degrees, isn't it? Because it kind of is taking that polar air and diluting it on a pretty good clip over the course of the year with the warm air below us. So this means that all this oscillation that occurs up this latitude also cools the lower latitudes off and warms the upper latitudes, so it makes it more temperate across the board. Okay? Whereas the tropics, all that heat tends to just get trapped in that Hadley cell and stay there. In the temperate zone, you spread the heat out more evenly, which is why it's temperate here in part. Okay. So Alaska is warmer than you might think, and California stays cooler than it would otherwise. All right. Now we're also going to. This is a model of the atmosphere, but this is water, and the same sorts of general patterns occur in the ocean. Okay, so we can also, thinking towards when we start next week and the last week of class, we'll be talking about ocean circulation. Some of the same things that you're seeing in this tank go on in the ocean. So now, imagine this as the ice pack of the North Pole up here, and then this is the warmer water. Let's think about it. If we have really cold conditions under the ice, what's the water going to tend to do? It's going to do just what it's doing here, right? The ocean water is going to tend to drop, right? And head which way? In general, out towards the equator in some kind of complicated way, but it's going to in general head towards the equator. And then it warms up and rises. So the ocean also has this kind of vertical structure where polar water travels southward, warms up, and the surface water travels generally northward back towards the poles. Okay, cool. That's thermal circulation. Now, when you take seawater, which is salty, right, and you freeze it, what happens to the salt when you freeze salt water? Does it just freeze into the ice? No, because it almost completely excluded from the ice. The ice crystals don't want the salt in there. So as you freeze water, so the ice on the North Pole, is it salt water or fresh water? It's basically fresh water. Okay, so as the ice pack forms in the winter, where does the salt go? It just stays in the water. So is that water saltier than regular seawater?
Yes.
Right. Now, is salty water heavier than fresh water?
Yes.
Yeah, that's simple. So we have not only cold water up here, but it's very salty. It's extra salty. So it's heavier due to the cold, and it's heavier due to the salt. Right? So it's extra heavy water. So polar water is salty and cold, and drops therefore extra fast. Okay, so that's called thermohaline circulation. A good buzzword you can put in right up. You can say this could be a model of thermohaline circulation also. Haline meaning salty. It's from the Greek halos meaning salt. Okay, so like halogen is the Greek word for salt former, like chlorine. Chlorine is a halogen because it forms sodium.
So what are we going to say is our velocity for our Rossby number?
I don't know. What do you want to say? Anybody want to add it together?
I mean, that's like the dots aren't even moving relative to the...
No, you really have to kind of look at the cloud. Tim, you want to take a guess at what the velocity is since you're close? Put your head. I shouldn't bring the tall guy over. The tallest guy in the class.
It depends. All the ones in the center are really moving.
Hardly moving at all.
Yeah, the little group right here is moving.
So if we wanted to just keep this, I've been kind of simple in rounding it to the nearest order of magnitude. You want to round it just down to a tenth of a centimeter per second, maybe?
Yeah.
I like less than a half.
Yeah. Okay. Why don't we say?
Like those ones are moving.
Yeah. They're actually just a little bit big. There's in the board.
1 millimeter.
Yeah, we could. I think it wouldn't. If we want to round off 1 or 2, or no more than maybe 3 millimeters per second, I would say. It's definitely noticeably slower than 1. So you can, say it was noticeably slower. It was difficult to observe, but we're going to estimate it at X. Okay, now, the length scale is the same. The velocity is different, and the rotation is different. So everybody got the right rotation? Off the board there. What is it now? 0.52. Okay. And like I say, actually, if this is, and we're saying it's somewhere on the order of 1 to no more than 5 millimeters per second now. Okay. So now we'll see what you can go calculate with them. I'll just let you guys do that part of your report. You calculate your Rossby numbers yourself. Okay. Anyway, thermohaline circulation is really important in moving cold polar water down to the tropics, where it can warm up the warmer water, and then in turn that warmer water that moves up helps warm up the part of the world that's up in, for example, Norway is not one big frozen block of ice. It's like, why? Because the currents bring a lot of moisture and the air currents, but also the water currents bring a lot of heat to northern latitudes. Okay, but are we messing with the ice cap right now due to global warming? Yeah, didn't we set a record this year for the smallest ice cap in recorded history? So, what's happening to thermohaline circulation?
More cold water is being pushed down, some more warm water is being pushed back up.
Well, basically thermohaline circulation is caused by the formation of the cap. So if the cap doesn't form as much and it melts sooner, then you're actually messing with the thermohaline. You're actually shutting down the thermohaline. In other words, if the winter ever comes along where the polar ocean doesn't ever freeze over, which they say in your lifetime is actually a pretty good probability, probably not my lifetime, but in your lifetime it may be that the North Pole is never frozen, just isolated pockets of ice. Then what happens to the thermohaline circulation? It's not totally gone because there's still some cooling up there, but you've gotten rid of a big component of it, especially the salty part. You've eliminated the haline part of it. So we're basically messing with this. And we saw here that a fairly small perturbation of just a factor of, in this case it was a factor of 5, but not a whole lot of difference in rotation produced completely different flows. So that's what scares a lot of people almost more than anything else about global warming is the messing with the thermohaline circulation, they think might end up being, for a lot of people, a surprise, like, oh, this is what really screws up the Earth. when we mess with it, because it doesn't. With flows, it doesn't take much perturbation for it to shift from one pattern to a very unexpected other pattern. So I also want you to take that away. One little tweak of the knob here, and we got two completely different flow regimes. One little tweak of the ice cap, and we might get a completely different ocean circulation. For example, one of the consequences of loss of thermohaline circulation is the possible collapse of the Gulf Stream. It's entirely possible the Gulf Stream could just shut down. There are models that suggest that. And if that were to happen, what's going to happen in England? It's going to turn into Labrador. Okay, it's going to turn into Siberia. Okay, doesn't mean they'll all move out, but they're going to have to definitely adapt with bigger coats and forget the sheep. Okay, so anyway,
The sheep should be well insulated.
they'll just have to get fatter sheep, thicker, better insulated sheep. I don't know. But it won't be mellow, green, rainy England anymore. It will be tundra-covered England and tundra-covered Ireland, and so forth. Okay. And, I mean, also the same thing to a lesser extent could happen in the Pacific Ocean, because we get a lot of our warm water ultimately from the Coriolis current, which is the equivalent of the Gulf Stream on the Atlantic. We're going to talk about these currents next week. The Gulf Stream, the Coriolis, Peru current, the Agulhas current off of South Africa. So, anyway, so the ocean current stuff is to be altered in principle modeled by this sort of stuff, so just be aware of that. Okay, any other questions? I think we're done. Matt, you got anything more you want to announce? You want to check notebooks and stuff like that?
Weather implications, what other implications could be connected?